Okay, so in this video we're going to look over mass spectrometry and the test tube reactions. And so especially the test tube reactions, we're really going to quite highly link to the oxidation of alcohols thing that we looked at before. So for the test tube reactions, which we'll look over first, there's the four main ones you need to know about. So the test for aldehydes, alcohols, halogenoalkanes and alkenes. Those are the ones that you're expected to know in year 12. Now there's the two different tests you can do for aldehydes. Generally the most common one that we'll come across is the Tollens reagent. But you can also write about failing solution as well. Now Tollens reagent is basically just a mixture. It's silver nitrate with some other stuff in there as well. It's got some ammonia or something in it. And I think it's in one of the year 13 topics. You do need to know the exact formula and everything for it. But as far as we're concerned, at this level at least, it's just got silver 1+ ions. Now the aldehyde acts as a reducing agent, and so it's going to give the silver an electron, as all reducing agents do, and it's going to turn these soluble, so you've got aqueous, silver ions into silver metal, which is insoluble. So the aldehyde is going to reduce the silver from silver 1 to silver 0, and this is going to deposit silver on the surface of the glass where you do it in. So it forms a silver mirror. So this is sometimes called the silver mirror test. Now you need to acidify. The mixture beforehand. So if you add silver or silver nitrate into a mixture that contains hydroxide ions or carbonate ions, the silver reacts with those. So the silver reacts with OH and ends up forming silver oxide, and it can also form silver carbonate. So both of these sort of give a false result, where you're going to get a load of precipitate out because both of these are solids. Whereas you're looking for this silver being produced, the silver, pure silver, rather than silver carbonate or silver oxide. So you need to acidify to remove these. So you're generally going to use nitric acid. You don't want to use hydrochloric acid. You should know from your from previous topics that the chloride ion from hydrochloric acid is going to form silver chloride. There's a white solid. So you need to use an acid which has an ion that won't form a precipitate with silver. So nitric acid is generally the go-to. You probably could use sulfuric acid as well. And so by adding H plus from the acid, this is removed just to form water. And if you add the acid in, this is removed. It decomposes the carbonate ion into carbon dioxide and water. So you need to do this to remove any of the negatively charged ions that could interfere with the test beforehand. Now the failing solution contains copper 2+. Contains copper 2+ ions. It's blue. It's a lot like the Benedict solution that you come across in biology, even down GCSE. Now this gets reduced by the aldehyde as well to form copper plus. So we've got blue copper 2+, just like copper sulfate. It gets reduced to form copper 1, and this has a red colour. So we have a sort of red-brown precipitate that's formed, or at least it turns a red-brown colour. So for this, we're looking for it to go generally colourless to form a silver mirror, or for failing solution, we form a red-brown, a colour change from blue to red/brown. Now for alcohols, we're going to use the reaction that we saw for oxidation of alcohols as the test for the presence of alcohols, as there's a colour change associated with it. So with alcohols, you take your K2CR2O7 that's been acidified, and this has the orange colour of chromium 6. Now when that reacts with the alcohol, we form our carboxylic acid or our aldehyde in that reaction, or our ketone, and the chromium is reduced from chromium 6 to chromium 3, and this has a green colour. So we see a colour change from orange to green due to the reduction of the chromium ions. Now all of these are very highly toxic, so you need to be very careful when using this. So this will confirm the presence of a primary or secondary alcohol. It will not show any change with a tertiary alcohol. So they'll like to ask about that, where they might tell you, they'll give you the infrared spectrum, you identify it as an alcohol, and then they give you information about maybe the potassium dichromate test, and it's positive, and so you can narrow it down that it's not the tertiary alcohol, it must be a primary or secondary alcohol. Now, something that students always seem to forget is that it's not just alcohols that we come across that can reduce the chromium, that can react with the chromium ions. We saw in the previous topic that the potassium dichromate is perfectly happy to react with aldehydes. So this can react with RK2Cr2O7. The aldehyde is oxidized to the carboxylic acid. And our chromium again goes from chromium 6 to chromium 3. Now it's not a one-to-one reaction. Each aldehyde is not giving up the 3 electrons, but this overall is what's going to happen to the chromium ions. So this test is not selective for just alcohols. It also is going to test for aldehydes as well. But we can use the aldehyde tests to work out if it's an aldehyde or not. So if you're not sure if it's an aldehyde or an alcohol, you do the Tollens reagent on it. If it's an aldehyde, we'll get the silver mirror formed. If it's a primary or secondary or tertiary alcohol, this isn't going to happen. The alcohols, yes, they can act as reducing agents, but they're nowhere near good enough reducing agents to reduce the silver. The silver is not a very good oxidizing agent. The potassium dichromate is a very good oxidizing agent, so even the weakly oxidizing alcohols can reduce the chromium. The better reducing agent that is the aldehydes will also reduce the chromium as well. So you can't just use this test and go, aha, it's a primary or secondary alcohol. It could also be an aldehyde as well, so you need to watch out for that. So the next one is the test for halogenoalkanes. So if we consider chloro, bromo, and iodo ethane, we're going to test these. We're going to first react these with sodium hydroxide. So if we react these with sodium hydroxide, we'll get a nucleophilic substitution reaction taking place if we do it in water at a lowish temperature. Now each of those, it's going to form ethanol as the product, but we're also going to form what we've got our sodium ions hanging around, and we're going to form the chloride ions if it was the chloroethane, bromide ions if it was bromoethane, and iodo ions if it was iodoethane. And now you should know that these are pretty easy to test for from when you were studying halogen chemistry. Now we have sodium hydroxide, so there's going to be a mixture of our alcohol. We don't need to worry about that. The halogen ions, but also there's going to be some leftover hydroxide. So we need to remove that hydroxide by acidifying it. So we're going to add in some nitric acid to remove this. So we need to hydrolyze the molecules using sodium hydroxide. So step 1 is sodium hydroxide. Step 2 is we need to acidify it to remove any excess hydroxide ions. So HNO3. And then we're going to do, just as you would have done for test tube reactions for like pure salts of these, we're then going to follow that up with some silver nitrate. And that should precipitate out these different ions. So we form AgCl, AgBr, and AgI. We've got our different colours. We've got sort of our white, our cream, and our yellow, and then we've got the solubility of them. So off the top of my head, this one is soluble in dilute ammonia, this one is soluble in concentrated ammonia, and this one doesn't dissolve at all. I might be wrong. It's a long time since I've covered this. You should know better than me. That leaves us with the last one, which is the alkenes. Simplest one of them all. It's on the GCSE specification. So we take our ethene. You add bromine water to it, so bromine dissolved in water. Be very careful with it because bromine is not very pleasant stuff. we form the dibromoalkane, so we just get electrophilic addition. Now this has a brown colour. There's a sort of faint brown colour from the bromine dissolved in the water. This is colourless. Most of the alkenes are going to be colourless, and it forms these, which are also colourless. So observation is we decolorise the bromine water. So you want to say it goes from brown to colourless, or the brown bromine water decolorises.